Hello everybody, welcome. I'm Bharat Acharya. Welcome to my video. Today I'm going to teach you 𝗕𝗵𝗿𝗁 architecture. Okay, there's been massive demand for this video. Most people learn 𝗕𝗵𝗿𝗁 as a processor, as their starting processor. So I hope this video is really helpful to you. I'm going to put in my best. It's going to be a little long video because the architecture is big and you need a lot of background to learn it. But I said I'm going to put my best. Let's see. Let's start. Now, before we start with the architecture, a few basics that you need to know. I'm sure you would know it, but still it's my job to just cover them up. 𝗕𝗵𝗿𝗁 is a 16-bit processor. What does that mean? It can transfer 16-bit data at a time. It operates on 16-bit data at a time. It has an ALE which is of 16 bits. So every activity that 𝗕𝗵𝗿𝗁 does, it is capable of working on 16 bits of information in one operation. In other words, in one cycle. Okay, keep that in mind. Now let's start. Come on, look at the whole architecture. The first thing that you notice in the architecture is divided into two units. Can you see that? This upper section is called as BIU. BIU stands for Bus Interface Unit. I say again, Bus Interface Unit. The lower section, where all the action takes place, is called the Execution Unit, EU. So your architecture has a BIU and EU. So the first question, why is the architecture divided into two units? The answer is because of pipelining. There is a concept called as pipelining. I've covered that in a video before this. I'll be giving you the link as a suggested video right now. In case you've not seen it, please check it out. You need to know that. You need to know what's pipelining to understand the architecture. If you don't know, I'll just give you in a nutshell. Normally what a processor does, the processor before 𝗕𝗵𝗿𝗁, that was 8085, how it worked? It would fetch one instruction, get it inside the processor, execute it, finish it, then go and fetch the next instruction. So it used to work on one instruction at a time. In 𝗕𝗵𝗿𝗁, it's not like that. It will fetch one instruction from the memory. Then, while executing that instruction, it will side by side fetch the next instruction. That means it's working on two instructions at a time. One instruction is being executed and the next one is being fetched in advance. What is the advantage? You are saving time. So what happens? Normal processor works like this. Fetch, execute, fetch, execute, fetch, execute. 𝗕𝗵𝗿𝗁 works like this. Fetch, execute, 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 only executions. Yes, it is fetching, but that fetching happens alongside. So the way it works is, the upper unit, BIU, will fetch the instruction from the memory. Then it will pass the instruction to the execution unit. While the execution unit is executing that instruction, BIU side by side will fetch the next instruction. That means the architecture is doing two things at a time. That's why the architecture is divided into two units. One unit for fetching and the other for execution. Tell me, did you understand this much? I hope you did that. Now, we learn the architecture unit by unit. But one small thing. Before you start seeing this big diagram, and then I always tell my students, I teach everything from 8085 up to Pentium, advanced versions, Spark processors, etc. I tell everybody, no matter how big or complex the architecture looks, remember, at the end of the day, it's a processor. What does a processor do? Fetch, decode, and execute instructions. So any architecture you pick up, just trace the path. How do you fetch an instruction? Where is it getting decoded and where is it getting executed? If you can trace the path, you can understand every architecture in the world, every microprocessor architecture. Okay? So, coming back. When you look at this architecture, you'll notice everything in the architecture is rectangular in shape, except for this object and this object. Now both these objects have the same shape, it's just drawn upside down, the shape is the same. Now what is this symbol? Whenever you see a symbol like this, remember, this is the diagram of an arithmetic circuit. There is some arithmetic taking place over here. What does it mean? These are the two operands. This is where the operation will be performed. And this is where you produce the result. 2, 3 plus 5. You're doing 2 plus 3, the result is 5. Now, you see, sorry about that sound. I don't feel irritating. Okay, so you see two such symbols on the board. There's one here and there's one here. So both of them are arithmetic circuits. Are both of them the ALUs? No. There is only one ALU. This is the ALU. So, if I write an instruction like add BL, CL. I know I have not taught you what are BL and CL, but come on, you can understand that my purpose over here is to add two registers. This addition will be performed by this ALU. So, if the ALU is doing this addition, what is the arithmetic operation that is taking place over here? There is something happening here. What is it? Here, we are doing calculation of physical address. Physical address is calculated as segment address multiplied by 10 plus offset address. Do not get bogged down. Yeah. I know you'll be wondering what is this all about. You will understand. Just be patient and keep concentrating. Leave aside everything else. If you're looking at this and side by side chatting, no, it's not going to work. I need your concentration to understand what's going on over here. Now, when you learn the architecture, it's assumed that you know something called as memory segmentation. Now, I don't want to make that assumption. I have made a video for that too. The video is there in my channel. Just check it out. You will get it. If possible, I'll just put a suggested link right now. So I'm summarizing that whole video of segmentation in 2-3 minutes. You need to know that. Otherwise, you'll just be mugging up the architecture. If you want to understand the architecture, you need to know segmentation beforehand. Now, this is the entire memory supported by 8086. This is the processor, this is the memory. Memory is not inside the processor, it's a separate entity. The amount of memory that you can access depends on the address bus. 8086 has a 20-bit address bus, so it can access 2 raised to 20. That is 1 MB memory. So this entire memory size is 1 MB. Okay? Now, just like your hard disk is of 1 TB, I'm putting a lot of things into a small discussion. Okay, just pay attention. Your hard disk is 1 terabyte as an example. That means there are 1 trillion locations. You tell me, do you know the address of every location? You want something from the hard disk. Do you know the real address of that location? 1 out of 1 trillion numbers. Do you know that? No. Do you want to know that? No. Who cares? How do you access every location? For you, whatever you want to access is there in some file. Tell me, do you understand this? Everything you want to access from your computer's memory is inside some file. So for you, its address is the folder name and the file name. I repeat, folder name and file name. Once you give folder name and file name, you go to the location you want. That is a virtual address. That is not the real address. Please understand, we have given the folder name, we have given the file name. In the memory, there is no folder, there is no file. In reality, there are 1 trillion locations and every location has its own address. But you as a programmer don't want that headache. You want the simplicity of folders and files. Exactly the same thing. Instead of having one raw memory of 1 MB, the memory is divided into 4 sections called as segments. They are called code segment, stack segment, data segment and extra segment. Code segment contains a program, stack segment contains a stack, data and extra segment contain random data. Any kind of data that you want to store in a random form is stored over here. Now, if you want to access some location, hear me out clearly. Any location you want to access will have its own unique address, its genuine address, its physical address. That physical address is 20 bits. We don't give that address. Like you've used your computer for so many years, but you don't know the physical address of anything because you as a person, as a programmer, as an end user, you don't give that address. You give a virtual address, which is a folder name and a file name. Similarly, we give a segment address and an offset address. I say again, a segment address and an offset address. Segment address gives the starting address of the segment. Whatever you want to access is a part of a segment. Whatever you want to access in your computer is a part of a file. So you give the file name and then you go to the location within the file. Similarly, you give the segment address which tells you where the segment begins, and then you give an offset address which just tells you the location within that particular segment. So for code segment, stack segment, data segment and extra segment, CS, SS, DS and ES will give their segment addresses, and IP, SP, SI and DI will give their offset addresses. This is the segment address, this is the offset address. I'll give you another simple example. There is a book. No, I'm not talking about my book. Okay, I'll talk about my book later. There is a book which has 1000 pages. You want to go to page number 4564 as an example. That is its real address, the physical address, the actual address. It's 564. But you can also say it as location 64 of chapter 5. Assuming every chapter is 100 pages, chapter 5, location 64 is again 564. So chapter 5 is like your segment address, telling where you began. So it's telling where the segment began. So it's like these are chapters in a book, and within that chapter this is your offset address. So this is segment address and offset address. When you give them, the processor does a small operation on them using a small formula, and calculates the physical address. This is a formula. Physical address is calculated as segment address multiplied by 10 plus offset address. Segment address is given by CS register multiplied by 10 plus offset address given by IP. Assume the segment address is 1000 and the offset address is 2345. Come on. 1000. Assume CS is 1000 and IP is 2345. CS is your segment address, IP is your offset address. Combine the two. 1000 multiplied by 10 is 10,000 plus 2345 becomes 12345. That is how the processor calculates the physical address. Let's do some examples. Suppose segment address is 2000, offset address is 4000. What is the physical address? 2000 into 10, 20,000 plus 4000 makes it 24,000. Segment address is 5000, offset address is 5000. Physical address should be 5000 into 10, 50,000 plus 5000 makes it 55,000. Tell me, did you all understand this? So, this is how processor calculates the physical address. Does it need to? Of course it needs to. The real address is the physical address. You want to access a folder and a file in your computer. That's your convenience. A folder name and a file name both given by you, both chosen in such a way that you can remember them easily. Neither the folder name nor the file name is the real address. The real address is the physical address of that file, which you till now don't know. But somebody needs to calculate it. So that's calculated by the processor. That's it. This is the background I wanted you to have. I know you spent 5-7 minutes till now, even the architecture is not started. But you needed this, otherwise you won't understand the architecture. Now let's start. Now you'll understand the whole architecture, that's my guarantee. Okay. So these are the 2 units of the architecture. Now you tell me, if you understood the discussion that I just said, who needs to calculate physical address? The EU or the BIU? Who is going out to fetch instructions? EU or BIU? BIU. So, whenever EU is executing an instruction, at that time, BIU wants to fetch the next instruction, for which BIU needs to calculate its address. That is calculated over here in this section. So that is done by this circuit. Physical address calculated as segment address multiplied by 10 plus offset address. So do you understand what these 2 objects are doing in the architecture? Okay. Now, long time back, 19 years back, when I was a student like you and when I was learning the architecture, the first time when I saw this architecture, the first thing that came to my mind was, this is also an arithmetic circuit, this is also an arithmetic circuit. Then why do you have 2 circuits? Why not do both calculations in the same circuit? That will reduce hardware. The answer is because you want to do pipelining. We want to do 2 things at a time. This ALU is busy. I'm sorry about that. So while this ALU is executing this instruction, at the same time, we want to fetch the next instruction. So the BIU will calculate the physical address. If both calculations were done by the same circuit, you would not be able to do both at the same time. So there would be no pipelining. So to do pipelining, they are both independent circuits. Okay? Now, so it's calculating physical address. Now we're going to focus on BIU. We're going to stay focused on BIU for about 10 minutes and then we go to EU for 10 minutes. 20 minutes, I think we should be done. Let's see. BIU, what are its functions? First, most important function, fetch the next instruction. Second, calculate the physical address. Third, manage this object called as the queue. Now we'll come to this queue. One second. Let's just quickly revise what are these. I hope you paid attention. Go on answering. CS, SS, DS, CS. What are these? Code segment, stack segment, data segment, extra segment. No, these are not the segments. This is a mistake everybody makes and then they stop learning the architecture because everything goes for a toss in their mind. These are not the segments. Segments are present in the memory. Okay, remember I taught you all segments are there in the memory. These are segment registers. They contain the addresses of all the segments. I repeat for the last time, they contain the addresses of all the segments. They are all 16-bit registers. CS tells where the code segment begins in the memory. SS tells the starting address of stack segment. Similarly, DS for data segment, ES for extra segment. Are you clear? They give the base address, the starting address, the segment address of the 4 segments. IP stands for instruction pointer. It contains the offset address. It contains the offset address within the segment. So this is your code segment. Okay, come on, look here. This is your code segment. CS gives it starting address. You've done that. You've given the address. Now, for every instruction, what is going to change? The segment address or the offset address? Come on. Absolutely, the offset address. That means who is going to change? CS or IP? Yes, if you're saying IP, you're understanding it. as every instruction goes on getting fetched, IP goes on getting incremented. That's how IP always points to the next instruction. That's what IP is. It always gives the address of the next instruction. Which address? Offset address. CS gives the segment address, IP gives the offset address. Both of them are combined over here to calculate the, come on, B, answer. Both of them are put together to calculate the physical address. This is the physical address of what? Of the current instruction or the next instruction? Next instruction. The address, the instruction that we are about to fetch. So both of them combined together, given to the memory, the physical address. From there, from the memory, the instruction is fetched inside through the data bus. I repeat, through which bus? Data bus. There are three buses. Address bus, data bus, control bus. On the address bus, we gave the address. From the control bus, we gave a read signal telling that we want to fetch. The instruction will come inside the processor through the data bus. I'm saying for the last time, through the data bus. Data bus is 16 bits. Remember when we started the video, I told you 8086 is a 16-bit processor. So the instruction is coming in through a 16-bit data bus. That instruction comes inside. Now, we have fetched this instruction. Are we going to execute it right now? No. This is a pipeline processor. Some execution is going on. We have fetched the next instruction in advance. That fetching in advance is called as prefetching. Okay? Prefetching. Come on, you understand the word. So, instructions which have been fetched in advance, which have been prefetched, come and get stored into this object called as 6-byte prefetch queue. I repeat, 6-byte prefetch queue. What happens? All future instructions come into this queue. EU wants to execute instructions. It will go on removing instructions one by one from the queue. As EU removes instructions, BIU fetches more instructions and puts them into the queue. Understand, for the last time, BIU goes on fetching, puts them on the back side of the queue, instructions move ahead, come out to the EU. As EU removes more instructions, BIU goes on adding more instructions into the queue. Did you understand this much? Now, a few things to understand over here. First of all, what's the size of the queue? The queue is of 6 bytes. What does that mean? Let's see. Let's move on this side. Remember pipelining? Pipelining means while we are executing an instruction, we are also fetching the next instruction. Now that's the definition. In reality, what happens is this. Suppose these are instructions of a program. Currently, we are executing the first instruction. While we are executing the first instruction, BIU not only fetches the next instruction, it fetches the next 6 bytes of the program, and stores them into the queue. So, somebody asks you, how many instructions are there in the queue? No one knows. How many bytes are there in the queue? 6 bytes. 6 instructions and 6 bytes are two different things. All instructions are not of the same size. Instructions can be of 1 byte, 2 byte, 3 byte, 4 byte, 5 byte, going all the way up to 6 bytes. The biggest instruction in 8086 is of 6 bytes. No wonder, that's the reason why the queue is also of 6 bytes, so that it can hold the biggest possible instruction. Now, in case you're wondering how different instructions are of different sizes, I'm just giving you a glimpse, an idea. This is going to help you in understanding machine language more. I've taken 3 instructions, they are of different sizes. First instruction, move BL, CL. What does this do? CL register's value comes into BL. BL gets the value of CL register. Okay. Move BL, 25. BL register gets the value 25. Move BX, 2000. BX register gets the value 2000. Now hear me. This is all assembly language. Okay? We type assembly language. Then we give this program to an assembler. The assembler converts it into machine language and puts the program into the memory and gives it to the processor for execution. So, we have typed in assembly language. Every instruction, when it converts into machine language, it becomes a series of zeros and ones. The binary pattern 00110101 indicating the operation that we want to perform is called its opcode. I say again, it's called its opcode. So, every instruction has its own unique opcode. Tell me, did you understand this much? There's an opcode for move, there's an opcode for add, there's an opcode for subtract, etc. etc. Now, hear me. There is an instruction move BL, CL. This is which language? Please answer. This is assembly language. When converted into machine language, it will have an opcode. So the point I am trying to make here is, there is an opcode for move BL, CL. will there be an opcode for 𝗵𝗶𝗶𝗃 or for 𝗵BL? Come on, think about it. Think about it. Will there be an opcode for 𝗵𝗶𝗃 or for 𝗵BL? Yes, there is an opcode only for 𝗵BL. There cannot be an opcode for 𝗵BL_25 because 25 is a number. If you have an opcode for 𝗵BL_25, you will need one more opcode for 𝗵BL_26. Come on, it's not rocket science, it's so obvious. You'll need another opcode for 𝗵BL_27. That means you require infinite opcodes just for 𝗵BL. That is not possible. One instruction cannot take away so many opcodes. So, what did you understand? A number is never included in the opcode. Say this again in your mind. A number is never included in an opcode. Opcode specifies the operation. Opcode specifies registers. You can have opcodes for registers. You can have opcodes for operations. You can never have an opcode for a number because a number has infinite options. Registers are limited. Operations are limited. Numbers are too many. Are you clear? So in this instruction, there is just an opcode. In this instruction, there is an opcode and an operand. 25 is written separately as an operand. In this instruction again, there is an opcode and an operand. So this is the smallest of these instructions, only has an opcode. This instruction has an opcode with an 8-bit operand. 25 is an 8-bit number. This instruction has an opcode but a bigger operand, a 16-bit operand. So it's a 16-bit operand means 2 bytes. This is 1 byte. So all I'm trying to make you understand is different instructions have different sizes. Some just have an opcode, some have an opcode and an operand, an 8-bit operand, some have an opcode and a 16-bit operand, some have 2 operands, etc. So all I'm trying to make you understand is different instructions are of different sizes. I hope you understood that. So instructions can vary from 1 byte, 2 byte, 3 byte, all the way up to 6 bytes. Now, let's come back over here. While we are executing any instruction, the next 6 instructions or bytes, tell me, the next 6 bytes of the program are taken and stored into this object called a 6-byte queue. Tell me, did you understand this? Now, should this be a queue or a stack? You know there is a difference, right? Please tell me you know that. A stack works in the manner last in, first out. A queue works in the manner first in, first out. So the order in which instructions are fetched should be the order in which they are executed. So this should be a queue. Had it been a stack, program would be fetched in this order but be executed in the reverse order. That is obviously stupid. So this is a queue. It's of 6 bytes because the biggest instructions are 6 bytes. Now let's take a few examples. Suppose they are all 1 byte instructions. Okay? That means there are 6 instructions. I hope you understand. EU was executing some instruction. The execution unit was executing some instruction. That instruction is over. EU wants a new instruction. Where will it take that instruction from? From the memory or from the queue? Yeah, from the queue because they've already been fetched. As EU goes on removing instructions, the queue will go on becoming empty. When the first instruction goes out, the remaining 5 move ahead, so this byte becomes empty. Then again this byte will become empty. Slowly the queue will go on becoming empty. Sometime or the other, BIU will have to refill the queue. When will BIU refill the queue? One option, very laid back option. We'll wait for the whole queue to become empty, then we'll refill it. Is that a good idea? Obviously not. What does that mean? If the queue is empty and EU now wants a new instruction, it will have to wait for instructions to be fetched. We don't want that to happen. So what happens is, the moment 1 byte of the queue becomes empty, BIU will refill the queue. No. If 1 byte of the queue is empty, BIU will not do anything. It will wait for 2 bytes to become empty to refill the queue. Why does it wait for 2 bytes to become empty? Come on, I've given you the answer. If you paid attention to the video, I've given you the answer. 2 bytes means 16 bits. 8086, yes, if you're answering this, I'm with you, shabash. 8086 is a 16-bit processor. It can transfer 16 bits, means it can transfer 2 bytes in 1 cycle. So why should it waste 2 cycles? If it sees 1 byte is empty, it does not bother. The moment it sees 2 bytes are empty, it goes to the memory, fetches 2 bytes and puts them into the queue. So that the queue is full of instructions. Did you understand this? One last point. Okay, over here students get this down. Right now 2 bytes are empty. Okay, listen to me. 2 bytes are empty. As per the discussion we had, BIU should fetch the next 2 bytes and put them into the queue. That means it should fetch the next instruction. Now suppose the forthcoming instruction is a 4 byte instruction. If you fetch it, Will you get full instruction or half instruction? Of course, you get only half. So my question is, will BIU get this half instruction? Yes. Why? This half instruction is not going to cause any problem. It's not its turn right now. You can't jump the queue. Right now it's the turn of this instruction. By the time this instruction comes over here, it will be a full instruction. Because the queue is of 6 bytes and the biggest instruction is 6 bytes. So my point is, while fetching, BIU does not know and does not care whether the forthcoming instruction is of how many bytes. It follows a simple principle. The moment 2 bytes are empty, it will go and refill the queue. Tell me, did you understand this? Last point about the queue, and then we are done with BIU, we go to the next unit, queue. Pipelining. Is it a useful idea? You tell me. Is it worth doing pipelining? We are executing one instruction side by side, fetching the next instruction. Is it going to save time? Of course it's going to. That means this execution will happen non-stop because in the background fetching is already taking place. So the good thing about pipelining is that it saves time. That's the advantage. There is a drawback of pipelining, which I have discussed in my pipelining video. I'd shown you the link earlier. Pipelining assumes that the program will always go in a sequential manner. Look here. We were executing instruction number 1, 2 to 7. These bytes are prefetched and kept in the queue, assuming that the program will go in a sequential manner, which is true. Most of the times programs go in a sequential manner, but not always. Suppose the first instruction decides to do a jump to location number 9. Now, after the first instruction, who should be executed? You're right, 9th, because the first instruction has jumped. But while first was being executed, 2 to 7 are there already present in the queue, assuming program will go in a sequential manner. Since we have taken a jump, all these instructions are now valid or invalid? They are invalid. That means the instructions which have been fetched in the queue have to be discarded. That's what we say. Pipelining fails when there is a branch because it assumes program will go in a sequential manner. If there is a branch, whatever has been fetched into the queue is invalid and immediately has to be flushed, discarded, cleared. Any word you like, you can use. It all means the same thing. Do not misunderstand. When I say the queue is cleared, I am not saying that we are deleting the instructions from the program. They are very much there in the program. If required, they can be fetched again. But right now, they are not required to be in the queue. So the queue gets discarded. Now what? Does pipelining stop? No. The processor goes to the new location, fetches 6 bytes, puts them back into the queue and continues pipelining as usual. Only momentarily pipelining fails whenever there is a branch. Tell me, did you understand this? Yeah? So that finishes the BIU. 1 minute recap and then we go to the EVA. What are the functions? Calculate physical address, transfer data with memory, fetch instructions, manage the queue. Management of the queue is done by the BIU. Okay, what's the size of the queue? Come on, 6 bytes. Why is it 6 bytes? Because the biggest instruction is of 6 bytes. When is the queue refilled? When 2 bytes are empty. When is the queue discarded? Whenever there is a branch. What are CSS, DSES? Please say this correctly. Please say this correctly. What are they? Are they the segments or are they segment registers? Yes, they are segment registers. The segments are present in the memory. The segment registers are present in the processor. They contain the segment addresses of the 4 segments, the starting addresses in very simple language. IP, instruction pointer. What does it contain? It contains the offset address. I repeat, the offset address of the next instruction. When we want to fetch instructions, we need CS and IP. CS gives the segment address, IP gives the offset address. 𝗵𝑝 combines the two to produce a physical address using the formula segment address multiplied by 10 plus offset. That calculation takes place over here. That's all about BIU. Tell me, did you understand the BIU? I hope you did. Okay? Now, we come to the second unit, the execution unit. That is much lighter, so much easier than the BIU to understand. Come on, look at it, nothing. Execution unit has one track purpose, to execute instructions. It has nothing to do with the external world. All external operations are done by BIU. Execution unit just executes instructions. Now, where are instructions present? They are present in the queue. Come on, give me some basics. Every instruction, first of all, is fetched. We have done that. Then, not executed. Between fetching and execution, there is decoding. So the first thing we need to do is decode the instruction. The instructions which are fetched in the queue, one by one will enter the execution unit whenever their turn comes. So this instruction will first go to the control section. Listen carefully. We'll go to the control section where it will get decoded. We have written an instruction like, let's say, add DL, CL. Our intention is to add DL and CL. This is assembly language. What we write is assembly language because it's easier to write. What has come is machine language. So what has come is not this beautiful statement. What has come is 00110101. I'm just taking an example. This is called an opcode. So first, somebody has to make sense of this opcode. Somebody has to understand this opcode. That is called as decoding. That's done by the control section. Once it decodes it, it produces control signals. You don't show them because it makes the diagram impossible to read. But you got to understand it. It releases control signals. These control signals go everywhere in the architecture and they tell every object what operation has to be performed. Okay? So first instructions are fetched, then they get decoded. It informs everyone what has to be done, and then execution takes place. ALU, come on, so simple to understand. ALU, can the ALU add? Yes. Subtract, multiply, divide. It can do a lot of things. So should it do whatever it feels like? No, it should do what the instruction wants. But instructions are not coming in. Instructions are coming here. The control unit will decode the instruction and then tell everybody what operation has to be performed. I hope you understood what the control unit does. Okay? Look, control unit, control section means the same thing. Now, before you go to the ALU, let's first understand some registers. Come on. SP, BP, SI, DI. Come on, I need some effort from you. Come on, you're more than halfway through. You're 70% through. SP, BP, SI, DI. What are they? Yeah, they are registers. Everything is a register. What are they? They are called offset registers. Say again, what? Offset registers. These are called segment registers. IP was an offset register for code segment. These are also offset registers for different segments. SP and BP are offset registers for stack segment. SI is an offset register for data segment. DI is an offset register for extra segment. What do they give? They give offset addresses within those respective segments. Okay? More about them in the segmentation video. I would love to explain them right now. But then I'll just be deviating too much from the topic. As of now, I just want you to understand they are offset registers. They give offset addresses within the segments. Okay? Now, A, B, C, D. These are your friends. If you are a sensible person, the best concentration of this video should be here. Okay? I want you to understand these registers properly. If you see yourself learning 8086 in depth, if you see yourself becoming an 8086 programmer, you need to understand these registers. These are your best friends when you're doing programs. They are called general purpose registers. I say again, general purpose registers. What are they used for? I tell you, write a program to add two numbers, 4 and 5. What do? You first put 4 and 5 inside two registers. You add them. The answer will again come inside some register. And then you'll display that register. This is how programming is done. Okay? Now, the 4 and 5 that you want to put inside two registers, where will you put them? Are you going to put them in CS and SS? Don't be silly. They are not general registers. They have special use. They give the addresses of the segments. These are again special registers. They give offset addresses of the segments. These registers give nothing. They are given to you. They are freely available to the programmer to do programming. Did you understand this? So these are the registers which you use all the time. How many registers you have? AL, AH, BL, BH, CL, CH, DL, DH are 8-bit registers. So if you want to use them as independent 8-bit registers, you have 8 registers. As you can see, 1, 2, 3, 4, 5, 6, 7. If you want to combine them and use them as 16-bit registers, they are called AX. X means a combination of two. BX, CX, DX. Okay? So AX, BX, CX, DX, they are 16-bit registers. So you can use them as 4 16-bit registers or as 8-bit registers. Again, I'm sure you are smart enough to understand what do L and H mean. L and H means the lower byte and the higher byte. Let's say AX being a 16-bit register contains a number 1, 2, 3, 4. 1, 2, 3, 4 is a 16-bit number. 3, 4 is the lower byte, 1, 2 is the higher byte. So if you're putting 1, 2, 3, 4 in AX, that means AL contains 3, 4, AH contains 1, 2. You can use AL alone, you can use AH alone, you can use them together. Anytime they can be used as individual 8-bit registers or as a combined 16-bit register. Did you understand this? Let's play with them a little bit. Come on, look here, I've done all the hard work. You just have to look. That's it. Come on. Officially, we start learning instructions. Okay? Move CL, 34. What am I saying? Move into CL the value 34. So CL register gets the value 34. Is it valid? Absolutely. 34 is an 8-bit number. CL is an 8-bit register. Similarly, move CH, 12. CH gets 12. So what has happened? CH register has got 12. CL register has got 34, which means effectively CX register has got the value 1, 2, 3, 4. If you want, you can do this in a single instruction by writing move CX, 1, 2, 3, 4. CX gets the value 1, 2, 3, 4. Now, if you directly started learning 8086, you're damn lucky. If you're a person who has first learned 8085, you will understand how beautiful this instruction set is. 8085 was a very amateur attempt to make a processor. It had instructions like MVI for 8-bit operations and LXI for 16-bit operations. So many programmers spent months to just sort out this confusion. In 8086, you have one single instruction called as move. Everything is done by move, M-O-V. Whether it's 8-bit or 16-bit doesn't matter. The register name clearly indicates CL means 8-bit, CH means 8-bit, CX means you're doing a 16-bit operation. So move CX, 1, 2, 3, 4, CX register gets the value 1, 2, 3, 4. Tell me, did you understand this? Come on, some more. Move BL, CL. Half the people misunderstand this instruction. Move BL, CL means BL gets the value of CL. It's like writing BL is equal to CL in C programming. Now in C programming, if you write BL is equal to CL, who gets what? BL gets the value of CL. BL is your destination, CL is your source. In any language, you first write the destination, then you write the source. So this is your destination, this is your source. So BL register gets the value from CL. If CL was 25, BL will get 25. Will 25 be removed from CL? No. It will stay in CL but will also get copied, duplicated into BL. Okay? Similarly, move BH, CH. BH gets the value of CH. So, BH got the value of CH, BL got the value of CL, which effectively means BX got the value of CX. So, it can be done in a single instruction, move BX, CX. Clear? Comfortable with the instructions, with the registers? Let's start with a simple program. Program to add 0, 4 and 0, 5. I'm adding two numbers. Come on, this is like the hello world of our subject. It's the easiest program a person can get. Write a program to add two numbers. I'm adding 0, 4 and 0, 5. The answer obviously is 0, 9. I want to do it using BL and CL register. The result should come in BL. Come on, first of all, we will put the number 0, 4 in BL. Move BL, 0, 4. We'll put the number 0, 5 in CL. Move CL, 0, 5. I want the result. Come on, people. I want the result in BL. What should I write? Add BL, CL. What will it do? BL plus CL, and we'll put the result in BL. Had I written add CL, BL, it would produce the same result 9. But now we'll store the result in CL. So the first operand that you write is your destination. Tell me, did you understand this? Now, the same thing, we will do it in the architecture. That's it. With that, you'll understand the whole architecture. Come on. The first step we did was move BL, 0, 4. So BL gets the value 0, 4. Then we did move CL, 0, 5. CL gets the value 0, 5. Now that we did add BL, CL. Come on now. I've spent good 45-50 minutes with you. I want this answer from you now. I want the entire explanation of this instruction. Come on, be honest. It's payback time now. I've put in this effort, now you're going to do this yourself. Add BL, CL. I want the whole working of this instruction. Okay, I'm summarizing this whole video in the next 2 minutes. Come on, together. Where is this instruction stored? All instructions are stored in the memory. When you want to fetch this instruction, which are the registers which will come into picture? Tell me the exact working of this instruction. When this instruction's turn will come, first of all, this instruction has to be fetched. The two registers that will come into picture are CS and IP. CS will give the segment address, IP will give the offset address. Combine the two, 𝗕P will produce the physical address. It will give the physical address to the memory, fetch this instruction from the memory through which bus? Yeah, through the data bus. This instruction has been fetched. This instruction will go into the queue, right at the end of the queue. One by one, this instruction will keep moving ahead. Finally, it will come here. When it is here, it is ready for execution. Now, this instruction will first go to the control section. For what? For what? Yeah, for what? For decoding. What we have written is add BL, CL. What has come here is not add BL, CL. What has come here is the opcode. The opcode has to be decoded. On decoding, the control section realizes we want to add BL and CL. First of all, it will give a signal to BL to release its value 0, 4. The value will come out over here. Tell me, should somebody inform BL? Of course, because the instruction could have been add 𝗕𝗵𝗂𝗁 also. How would BL dream that it has to give the value? Someone has to inform. So the control unit will inform BL to release the value 04. Then it will inform CL to release the value 05. Then are you with me so far? Though both the values, I told you, these are not clips on which the ALU is hanging. These are the operands. Remember the beginning of the lecture. These two are the operands. This is where the result is produced. This is where the operation is performed. So, control unit has extracted the value of 04 and 05 from BL and CL. Now, control unit will inform the ALU that you have to add. It could have added, it could have subtracted, it could have multiplied, it could have done a lot of things. It will tell the ALU now you have to add because the instruction was add BL, CL. ALU will add them, the result will be 09. This result will not be floating in the bus. As soon as this result is produced, control unit will inform BL. Now, whatever is the value of this bus has to be captured. So it will capture the value 09. This is how the instruction is performed. Please tell me, did you understand this? What else happened? What else happened? While this execution was going on, this unit was not simply enjoying the show. This unit was fetching the next instruction, doing the same process all over again. That's how the architecture executes. Okay. So these are registers. Let's play with the registers a little more. Now I know you understood. I know it's been a long video. Just 2-3 minutes. Just want you to understand it completely. I wanted to add 04 and 05. Answer was 09. We did it using BL and CL. The result came in BL. क्या हो? लाइट बंद हो गई.
वीडियो चालू है सर.
फ्लैश लाइट बंद हो गया.
चालू है सर, कुछ हुआ नहीं है.
पक्का वीडियो चालू है? पक्का वीडियो चालू है?
हाँ सर.
सेकंड दिख रहे? सेकंड्स आगे बढ़. Yeah. So we wanted to add BL and CL. We wanted to add 04 and 05. We did it using BL and CL. Okay? Can we do it using BL and DL? Yes. Same thing. BL and DH? Yes. Using BL and AL? Yes. Using only BL. Let's try to do it using only BL. Come on, I'm just making it get a little better. That's all. How? First, we will put 04 in BL. Move BL, 04H. Then, instead of putting 05 in some other register, we will directly add 05 to BL. Come on, come on, come on. Add BL, 05H. That's it. When you do add BL, 05, you're doing BL plus 05 and the result will be stored in BL, which again means BL will get the value 9. Tell me, did you understand it? Now come on, be a good student and show me the entire working of this instruction. I'm not doing this for fun. You'll learn something new. I bet you within a minute you'll learn something new. This instruction, when its turn comes, it has to be fetched. Come on, we've done this like 3 times by now. Come on. How does it get fetched? CS and IP together combined form the physical address, gives it to the memory. The instruction is fetched to the data bus. It will come right at the end of the queue. By one, it will keep coming ahead. Now the instruction has reached here. Now tell me, is there a fundamental difference between add BL, CL and add BL, 05? If you paid attention throughout this video, if you've been a good student, you will know. There is an opcode for add BL, CL. There cannot be an opcode for add BL, 05 because 05 is a number. If you have an opcode for add BL, 05, you need another opcode for add BL, 06, and like this you require umpteen number of opcodes only for add BL. So the opcode is only add BL and 05 is an operand. So that's the difference. This instruction only had an opcode. This instruction has an opcode and an operand. Now you answer. Between the opcode and the operand, which one do we decode? Which one do we add? We will decode the opcode, we will add the operand. I say again, we will decode the opcode, we will add the operand. That is why there are 2 lines drawn over here. If you notice, come on, I'm not here to skip things. I want you to understand the whole diagram, so I'm doing all this. What is coming over here? The opcode, so that it can get decoded. What is coming over here? The operand, so that it can take part in the operation. Did you understand it? So our instruction add BL, just this part, the opcode will come here, the control section will understand we want to add the value of BL with some number which is going to follow this opcode. So it will inform BL, BL will release the value 04. The second number will directly come over here and come on this side of the ALU, that is 05. Control unit will inform the ALU it has to add, it will add the 2, the result will be 09, which will be put back in BL. So all I'm trying to make you understand is if you want to add 2 numbers, you can do it using 2 registers, you can also do it using 1 register. Did you understand? The last part of the architecture, there is something called as operand register. This is nothing. Operand register is a temporary register. Say it again, it's a temporary register. It is not available to the programmer, which means after this you will never see this register again. It's not used in programming. It's used by the processor for storing temporary values. Every processor has temporary registers which is used only by the processor. It's used in various of these. There are truckloads of examples. I give the simplest example where it is used. There is an instruction like XCHG. XCHG stands for exchange. Suppose I want to exchange BX and CX. The processor cannot, you understand what is exchange, right? The value should be interchange. The processor cannot directly take the value of CX and put it into BX because then it will lose the value of BX. So what does it do? It will take the value of CX, put it into a temporary register. We'll take the value of BX, put it into CX. We'll take the value from the temporary register and put it into BX. So the values will be exchanged. To do this, processor needs a temporary register, such a register which is not available to the programmer so that our values are not lost. So for such purposes, processor uses the operands register. This is one example. There are umpteen examples. Just take a simple one to make you understand. So it's not a register used by us. It's used by the processor for temporary storage. The last and final register. Come on, huge topic this has been. There is something called a flag register. I have made a video for the flag register. It is there in my playlist. Check it out. It explains all the flags in detail. Here I'm just going to give you an idea. The flag register has various flags. Each flag gives some status about the current result. I say again, status about the current result. There is a sign flag which will tell you that the result is positive or negative. There is a zero flag which will tell you whether the result is zero or not. There is a carry flag which will tell you whether there was a carry or not. Do you understand this information will keep changing after every operation? I have done one operation, it produced a carry. Carry flag becomes 1. I do another operation, it does not produce a carry. Carry flag does not stay 1. Now it becomes 0. That means flags change after every operation. So the flag register contains the status of the current result. Who produces the result? ALU. So every time the ALU does an operation, it produces two things. It produces a result and it produces a status. The result goes into the appropriate register. The status goes into the flag register. That's what flag register is. It gives you the status of the result. If you want to know the result, you check out your own register. If you want to know something about the result, many times you're not interested in the value of the result. Simplest example I can give you is compare. When you want to compare two numbers, how does the processor compare? It just subtracts them. If the result is positive, first number is bigger. If it's negative, second number is bigger. If the result is 0, both are equal. So here you're not interested in the value of the result. You want to know whether it's positive, whether it's negative, whether there was a carry, whether the result is 0. So for such information, you check out the flag register. I hope you understood it. So that's your whole architecture of 8086. As much as I could, I have covered it in the discussion. It's so different to teach this in the class. You have this liberty of time over here. Try to summarize everything in the video. All of this information in full depth is there in my book. I made this book after 18 years of teaching, as in I made it right in the beginning, but it just got refined and refined over the period of years. It contains everything that a person would want to know in 8086. If you're a student of 8086 and beyond, it has introduction to higher processors also, 𝗕𝗵𝗿𝗃, 𝗕𝗵𝗿𝗃 Pentium, but mainly focused on 8086. Everything right from the architecture to the instruction set to the programming, interfacing, to designing of the motherboard, etc. etc. The book is available on Amazon. The link for that is given below. Even the soft copy, in case you're not in India, in case you just like to save paper, which is a very good idea, I appreciate that. The software version, the Kindle version is also available. Again, the link for that is there in the description section. Check it out if you want more information about all this. This is about 250 pages. To cover all of this, I would require more than 100 videos, which obviously is not possible. So as much as possible, I'm covering up in videos, probably a few more videos of 8086 as soon as I can. I've been loving the appreciation that you all are giving. Thank you so much for that. Thank you for watching the videos and thank you for all your suggestions. I've been trying to put as many as I can into the videos, and it's just going to get better, hopefully. I hope you understood everything. I hope this video was worth your while. You paid a lot, you spent a lot of time on it. I hope it was worth it, and keep sending me suggestions and keep watching the videos. If you like it, just hit the like button, hit the subscribe button, as you please. Okay, wish you all the best. Do well.